Okay, so we talked about constant volume calorimetry. Now we're going to look at a reaction happening at constant pressure. So if the chemical reaction is happening in an open container, like a beaker or a flask, even a flask with a foil cover and a little tiny pinhole, the pressure inside where the reaction is occurring is the same as the external pressure, and so no pressure changes can occur. But volume changes can occur, and so the energy can evolve both as heat and as work. A lot of times, though, we're only interested in the heat exchange, and we really don't care about any work that is being done. So we have another term called enthalpy. It kind of sounds like you're lisping or something. And the abbreviation for this is capital H. E was for energy, that makes sense, but we ran out of E's, so enthalpy is H. This is the sum of the internal energy, E, and the product of its pressure and volume. So it's the internal energy plus the pressure times the volume, and that's the enthalpy. Enthalpy is also a state function, like internal energy is. Pressure and volume are also state functions. So the enthalpy change is also a state function. The enthalpy change is the heat evolved in a reaction at constant pressure. So the change in enthalpy, delta H, is equal to the change in energy plus P delta V. So delta E, we learned, is the sum of Q plus W, right? So here we've got, instead of delta E, we're putting in Q plus W. There's a P here on the Q because it's indicating this is occurring at constant pressure. So Q plus W plus P delta V. And so P delta V, let's just remind ourselves of these little relationships here. Delta E is Q plus W, and pressure volume work is negative P delta V. So for delta E, we're subbing in Q plus W right there. And then for P delta V, we could multiply this by negative 1. P delta V is equal to negative W. And so then this simplifies to the change in enthalpy is the heat exchanged at constant pressure. You do not need to be able to derive that equation, but I think it's helpful to see that, well, it's just, never mind.
So the change in enthalpy is equal to the thermal energy?
The change in enthalpy at constant pressure is equal to the heat evolved or absorbed, the heat, yeah. So delta H and delta E are similar in concept. They are often similar in value. Delta E is a measure of all the energy, heat, and work that's exchanged, whereas delta H is a measure only of the heat exchanged under constant pressure. So for the purposes of Chem 1A, we can treat them as being the same. And that's probably what will happen in your mind anyway. The distinction between delta H and delta E is very subtle, but it's there. So the difference, the reason that these two are different is that in reactions that either produce large quantities of gas or use up large quantities of gas, then the change in volume is really big, and this does become, the difference is significant. But most of the time, we can treat these two things the same. So lighters are usually fueled by butane. So it's a cigarette lighter. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? Well, we've got these two things here. So it says the heat, heat is, it produces 2658 kilojoules. So when we write that into math language, that's like putting it into your checking account balance on your statement. Is that going to be a positive or a negative for the system?
So if it's a positive for the surroundings, and it's negative for the system?
Yes, if it's positive for the surroundings, it's negative for the system. So here we're talking about the combustion of butane. We're looking at the reaction. Sometimes it's not clear what we mean as the system and what we mean as the surroundings. So if it's uncertain, it's always the reaction. So the reaction produces, the reaction gives off. So this is a negative. So Q is negative. And it says it does 3 kilojoules of work. So if it's doing work, is that positive or negative? How do you feel about doing work? More often negative than positive, right? When the system does work, it's negative. When work is done on or for the system, then it's positive. Like when people do work for you, you feel good about that, right? Yeah, big smile back there. Okay, so that's Q and W. And we're really not having to do any real math here. This is just about what are these things. So delta E, let's do that one first. Delta E is Q plus W, right? We learned that a while ago. So if we take these two negative numbers and add them together, which of these is going to be correct? C, right? So this is correct. Delta E is negative 2661, because that's what you get when you take negative 2658 and negative 3, you get negative 2661. So actually, that's the only possible choice. We don't even have to look at the delta H. Of course, we're going to look at it anyway. At constant pressure, delta H is equal to Q. So if Q is minus 2658, then delta H is minus 2658. So there were several choices. There are 3 choices here that are correct for delta H. The author probably intended for me to do that one first. I didn't.
So is delta H only equal to Q when it's under constant pressure?
Yes. Delta H equals Q under constant pressure. Well, actually, delta H also equals Q. No, I'm sorry, that's delta E. Never mind. Yeah, it's so confusing, the E and the H. Yeah.
Reduces 2,658 kilojoules of heat. Why is it negative?
Because think of yourself as the system. You're producing something, it's leaving you, right? So it's going away from you. It's a direction of stuff moving. For the surroundings, it's positive because the surroundings are receiving that much energy, but the system is losing. Does that make sense? You just have to kind of puzzle through it and ask a bunch of questions. And then, end of the day, you just kind of have to do your best and hope it's right. You have a 50% chance of being right with the sign. So exothermic and endothermic reactions. So the signs for delta H and delta E follow the same conventions. Yay, we don't have to learn 2 different conventions. If delta H is positive, that means heat's being absorbed by the system. Heat going into the system, into the reaction, is called an endothermic reaction. So this prefix endo is like into, going in. Thermic refers to heat. When delta H is negative, heat's being released, it's going out, and we have exothermic, exo like exit, going out or outside. The exit over there, that's the door you go out of, right? You should have heard about this before. So, chemical cold packs have, many of them are ammonium nitrate as a solid, and then we break the little seal inside and it mixes with some water. And when that process occurs, the cold pack gets cold. The pack, the water and the plastic around it are part of the surroundings, the reaction, which we cannot put our finger on. The reaction is the system. The reaction is absorbing moisture, absorbing heat, and so it causes the surroundings to become colder. And so you put that ice pack on your skin, and maybe you sprained your wrist, like in this picture. And your skin gets cold. Why does your skin get cold? Is this pack putting cold into your skin? No, it's pulling heat out. Heat is energy, kind of like light is energy, right? Darkness is the absence of light, right? So you can't like spread darkness, you can only take away light. You can't spread cold, you can only take away heat. So the reaction is absorbing heat, it's an endothermic reaction. The hand warmers, like we mentioned at the beginning of this chapter, are exothermic reactions of iron with oxygen. So those reactions are releasing heat into the surroundings. So you hold one of those and you feel that your hand is getting warm because the reaction, that like mysterious invisible thing inside of there, is releasing heat into the surroundings. Part of the surrounding is the heat pack itself. The reaction is releasing energy. Burning gas, natural gas. Ooh, there's a typo. Natural's gas. Oops, that is too big. Burning natural gas is an exothermic reaction. It releases energy. Any questions? So identify each process as endothermic or exothermic and indicate the sign for delta H. Now the trick to these is to identify what is the system that we're talking about. Because for all of these, it's endothermic for one, the system or the surroundings. You've got the system and the surrounding. It's endothermic for one and exothermic for the other. Just like when you're buying and selling stuff, it's an increase in money for one person and a decrease in money for the other person. So you have to identify with the right party here. So, an ice cube melting. The system is the ice cube. It's melting. It's becoming a liquid. How do you make, sometimes it's like, well, I don't know. How do you make it melt faster? You put more heat into it, right? So the ice cube melting is absorbing energy from the surroundings. So that's an endothermic process. Whoops, that's not what I meant to do. So this is endothermic. It's absorbing energy. So what's the sign of delta H? Positive. Dang it. So delta H is positive. It's greater than 0. Because if energy is going into the system, then its energy balance is going up. Just like money going into your bank account, the balance is going up. It's a positive. Nail polish remover quickly evaporating after it's accidentally spilled on the skin. Nail polish remover is mostly acetone. It's cold. It's cold. right? Colder than just room temperature. Anybody want to try it? Feels cold. Just like when you get an immunization and they take that little alcohol wipe and they rub your skin and you're like, ooh, that's cold. They didn't have that in the refrigerator. Why does your skin feel cold? Because your skin is losing heat to this process, right? So here we have a liquid evaporating. How do you make a liquid evaporate faster? You heat it up. Right? That's why when we have wet clothes, we put them in the clothes dryer and we blow hot air on them because that makes them dry faster than if we blow cold air on them, right? So something evaporating, going from a liquid to a gas, endothermic. And then what's the sign of delta H? It's positive. The system here is the nail polish remover. It's evaporating. If we think about your skin, for your skin, is this exothermic or endothermic? It's exothermic because your skin is losing heat energy to this process. Does that make sense?
How do you know, like, I'm
Yeah.
not by myself and I think skin, and so I got exothermic instead of
Right.
endothermic.
It is challenging. How do you know what do we mean as the system? And these questions are not always very clear. I would go with the first thing mentioned in the sentence, right? It's talking about nail polish evaporating. So the nail polish is evaporating regardless of what's surrounding that. As that happens, we can think about that evaporating. So any of the state changes, going from solid to liquid, liquid to gas, those all happen when you increase the temperature of something. Those are all endothermic processes. The opposite, where you take a gas and condense it into a liquid, or a liquid and you freeze it, those are exothermic processes. See, gas burning within the cylinder of an automobile engine. So we've got two things mentioned here, gasoline burning, and we've got the cylinder in the engine. What's our best guess as what's the system? The gasoline burning is intended to be the system. So the gasoline burning, is that going to be exothermic or endothermic? What happens to the surroundings when things burn? They get hot, right? The surroundings get hot because the reaction is giving off heat. So this is exothermic. And then delta H is less than 0. It's negative for the gasoline burning. It's positive for the automobile engine. Any combustion reaction, anytime there's burning, combusting, the reaction is exothermic. Any questions? Yeah.
So you said that the surrounding gets hot. So whenever the surrounding gets hot, it's going to be exothermic, but when it gets cold, it's going to be.
Yes. So the surroundings experiences the opposite of the system. So if the system loses heat, that heat has to go into the surroundings. So the surroundings is getting heat. That's an endothermic process for the surroundings. It's an exothermic process for the system. So sometimes it might be easier to think about, well, what are the surroundings experiencing? And the opposite is what the system is doing.
Well, so the ice cube is getting cold.
The ice cube is not getting cold, though. The surroundings are getting colder.
Oh, so that's exothermic.
Yeah.
Oh.
Yeah. So we've got two opposite processes, and you could focus on either side whichever one's easier to think about. Figure that one out, and then the other side is the opposite. And a lot of times it's the surroundings that we can experience. Like the nail polish evaporating from your skin. I could feel the acetone evaporating. My skin was getting cold. I could feel that happening. So what is that for my skin? My skin is losing heat. That's why it feels colder. Where's the heat going? It's going into the system. So it's endothermic for the nail polish, exothermic for my skin. You just gotta get them straight in your head. Once you get them straight, it's not too bad. Oops. So exothermic reactions give off thermal energy. Where does it come from? Well, there's two kinds of energy. There's kinetic energy and there's potential energy. The internal energy of anything is the sum of all of its energy, kinetic and potential. Kinetic energy cannot be the source of the energy in an exothermic reaction, because if that were the case, the temperature would fall. The temperature would go down because the system would be losing kinetic energy. Temperature is a measure of kinetic energy. So it's potential energy. As the atoms rearrange during this chemical reaction, their potential energy gets converted into thermal energy. So what happens is there are weak bonds that get broken. That requires some energy to go in and break those bonds. And then strong bonds are formed, and when strong bonds are formed, that releases a great deal of energy. So in an exothermic reaction, we've got weak bonds being broken, strong bonds being formed. In an endothermic reaction, the strong bonds are broken. That requires a lot of energy to go in. Weak bonds form, which releases a small amount of energy. But after that endothermic reaction, the products of that reaction now are higher in energy than the reactants were. And so if you react them, they're probably going to undergo an exothermic reaction. So chemical substances can be like batteries in a sense. They can store energy. The gasoline that's sitting in the tank of your car, unless you have an electric car, is holding energy. It's storing energy. And you release it in the process of running your engine. You can also release it in more destructive ways by it exploding or something, right? And if you have an electric car, where's the energy come from? It comes from the battery. Well, what's a battery do? How does a battery have energy? It's storing chemical energy. And there's a chemical reaction that occurs when the battery discharges and energy is released. Any questions? So an endothermic reaction happens in a flask. What happens to the temperature of the flask? The reaction is endothermic. So what's happening to the reaction? Heat's going into, right? The flask is not the reaction. The flask is around the reaction. The flask is part of the surroundings. So if the reaction is endothermic, energy is going in, what's happening to the flask? The temperature would be falling because it's losing energy. As it loses energy, its temperature will go down. So the temperature falls. And that is very much like the pre-lab question. Dang, I wish I would have heard this Monday. Yeah, sorry about that. So back to stoichiometry again. Yay! So the enthalpy change for a chemical reaction, enthalpy is H, change is delta. So this is delta H reaction. It's also called the enthalpy of reaction or the heat of reaction. So heat and enthalpy, we often use those words interchangeably. So this heat of reaction is an extensive property, meaning it depends on the amount of stuff, right? So if you think about burning a teaspoon of gasoline versus burning a gallon of gasoline? Is the energy given off going to be different? Yes, it's going to be very different. The amount of heat transferred depends on how much stuff is reacting. So we can indicate that in association with the chemical reaction. So here we have propane combusting, reacting with oxygen to form carbon dioxide and water. And when propane burns, it gives off a certain amount of energy, and that could be per gram of propane, per molecule of propane, per mole of propane, right? So by convention, what we do is, here's our balanced chemical equation, and then we show the heat of reaction over here, minus 2,044 kilojoules, and this is for the amounts in the equation as written in moles. So this much energy when 1 mole of this burns, when 5 moles of oxygen are combusted, when 3 moles of oxygen, CO2 form, when 4 moles of water form. Okay, so we write this over here, and we just understand that this is per molar amount listed in the equation. And that saves us from writing down a whole bunch of extra stuff, this convention. So this relationship, this is related to the molar amounts in the equation. That's our conversion factor between moles and kilojoules of energy. So if we had 3 moles of propane, we could figure out how much energy would be released when it burns. So let's look at this thermochemical equation. We've got 2 A's going to AA. I don't know what that represents, but delta H is given as minus 51 joules. So this is asking, what's the heat associated with the reaction of 6 moles of A? 51 joules is for how many moles of A? 2 moles of A. So if I had 6 moles, 6 is how many times bigger than 2? 3 times bigger. So then the energy is going to be 3 times bigger. And we don't really need a calculator here. 3 times negative 51 is still going to be a negative number. And so it must be C. Because this is the amount for 2 moles. And this is the amount for, that would be 12 moles. So that is the thinking about it way. We can also demonstrate dimensional analysis here. So 6 moles of A, and I want to find out how many kilojoules or joules of energy. So I can get this relationship of joules, whatever the energy unit is here, joules per moles of A. Moles of A is 2 moles of A. And the joules here is just whatever's written. So it's minus 51.0 joules. So 6 times minus 51 divided by 3 gets us minus 153. So the moles cancel out. It's negative because delta H here is negative. The question here, what is the heat associated with? Does that convey direction? No, it means that, okay, there's energy being moved when this happens, but it doesn't tell us the direction. If it says, what is the heat released by the reaction of 6 moles, then the writer of the problem would probably expect you to express that as a positive number, right? Released. Because how much money did you spend? Minus $10. No, you spent $10. What does that show up in your checking account? Minus 10. Well, then how is it positive? Well, I spent 10. Spent, the word stands in for the minus sign. Any questions? Well, here's a more real example. Ammonia reacts with oxygen according to this equation. We've got the chemical equation there, and we've got delta H. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. We have a chemical reaction, and we have information about amounts of two different things. We have 155 grams of ammonia, and we want information about something else. Here it's the heat. So this is stoichiometry, even if we didn't have the title up there. And for stoichiometry, we do grams to moles to moles to grams. Right? Grams to moles to grams. And then we have to look at the specific problem and see, is this a variation, and if so, what's being changed? So 155 grams of NH3. So 155 grams of NH3, and it's asking for the heat. Well, which of those pieces of that represent heat? The delta H, I guess. So you could, over here, under here, write how many kilojoules. That's what we're trying to find. So, can we start with grams of something? Yeah, we've got grams of this. We'll go grams of that to moles of that. And then, do we need to go to moles of something else? We don't, because 4 moles of this gives 906 kilojoules. So I don't have to convert moles of this to moles of that and then to kilojoules. I just convert directly from whatever I was interested in to the energy. So I can cross off the last 2 steps and go directly to kilojoules. There's still moles in the middle, but it's just 1 mole this time. So that's my path, grams to moles to kilojoules. Any questions about that? I think one of the things that messes with your mind is that we've always done moles of one thing to moles of another thing, right? Moles of reactant to moles of product, or vice versa. There's always been 2 things. And here, there's only 1 chemical that we're talking about, 1 substance. Because this relates to each of these directly. And so going to moles of something else would be an extra step that we don't need to do. So grams to moles to moles to grams. Sorry, grams to moles to kilojoules. This is in my head. 155 grams of ammonia, NH3. I'm going to convert that to moles of ammonia. Put grams down here so they cancel out. And then I'm going to kilojoules. Kilojoules per moles of ammonia. I'm getting the units in there first, and then I'm going to stick in the numbers. So this last one comes from the delta H and the coefficient in front of ammonia. So 4 moles of ammonia gives minus 906 kilojoules. Minus 906 kilojoules. And then I need the molar mass of ammonia. I'll just save time at 17.034. So 155 divided by 17.034 times negative 906, and then don't forget to divide by the 4. Syntax error. What did I do? Oh, I got an extra decimal. I don't think I trust that. Oh no, I don't trust that number. I came up with minus 2.06. I'm like, wait a minute, that's too small. I accidentally had 0.155 grams. So minus 2061. I should have 3 significant figures. So there's 3 sig figs. I'm going to carry an extra 1 kilojoules. And then rounding this. I'd actually rather have you not round it than round it and change it to 206. It's not 206, it's 2060, right? I'm rounding in the tens place. There's the ones and tens and hundreds and thousands. I'm rounding here, and so if I'm going to keep it in decimal notation, I need to hold the place of the decimal point. And so I can call this negative 2060 kilojoules. Or it's better to put it into scientific notation, and then you don't have to worry about it. So my equation gave me a negative number, and then I'm going to go back and look at the question to see if I should keep the negative or not. It says calculate the heat associated with. That doesn't convey direction. So then I need to indicate direction with the sign on my answer. So it could be one or the other of those. Any questions? Minus 2.06 times 10 to the third. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And what mass of CO2 is produced? So here, we're mixing it up, and we're given information about the energy, which I'll just write over here because there's no better place to put it. And then it's asking me how many grams of butane. And you might say, well, I don't know what butane is. Well, that isn't butane, that isn't butane, and that isn't butane, right? This is water, carbon dioxide, oxygen's got to be this one. So question mark, grams. What's weird about this chemical equation? It's got a fraction in it. It's okay. We'll just use the equation as it's written. Don't mess with it. So here, the variation from grams to moles to grams. Am I starting with grams? No. Am I ending with grams? Yeah. I'm ending with grams. And so grams of butane comes from moles of butane. And then, do I need moles of something else? What I'm given is kilojoules. So this is saying that that many kilojoules of energy is equal to 1 mole of butane, because the coefficient here is a 1. So this much energy, wait a minute, sorry, that's what I'm starting with. This is equal to 1 mole of butane. The delta H here is equal to 1 mole of butane, 13 halves of a mole of oxygen, 4 moles of CO2, 5 moles of H2O. Okay? So for this first one, I'm not going to start with grams or moles. I'm going to start with kilojoules and go to moles and then to grams. Because kilojoules is what I was given. 1.5 times 10 to the third kilojoules to moles. So moles of butane. Kilojoule down there. So the kilojoules cancel out. And then I want grams. So grams of butane from moles of butane. And the moles cancel out. So what's the relationship between kilojoules and moles of butane? Yeah, minus 2,658 kilojoules is equal to 1 mole of butane. So 1 mole of butane is minus 2,658 kilojoules. And then we need the molar mass of butane, 4 times 12.01 plus 10 times 1.008, 58.12. And so we type this in 1.5 EE3 divided by negative 2,658 times 58.12. Oops. And I get negative 32.79 grams. Is that okay? No, we can't have negative mass. What'd we screw up? It produced this amount of energy. If the reaction produced that, and we're losing directional words, and we have to replace it with a sign, would that be minus or positive? It's negative. So this is actually negative 1.5, because the reaction is producing, it's giving off. So it's minus 1.5 divided by minus 2.6. And so then I end up with a positive mass, which I'm much happier with. So that's going to round to 33 grams of butane. And then there's another question, what mass of CO2 is produced? So we're going to do a similar process, but kilojoules to moles of CO2 to grams of CO2. Or you could take grams of octane and go to grams of CO2, but we're demonstrating this delta H thing. So going to moles of CO2, kilojoules of energy, well, it's still minus 2,658 kilojoules of energy, but for how many moles of CO2? For 4 moles of CO2. And then converting to grams. And just remember that one. Negative 1.5 EE3 divided by minus 2,658 times 44.01, 24.83. Which would round to 25 grams of CO2. Any questions? Yeah. Yeah, even if it doesn't say it's producing negative 1.56 or 1.5 times 10 to the third kilojoules, we have to understand that we're just talking about something moving directions. So some of you are going to be okay with that, and some of you, I think, are finding that just to be very disturbing. Right? It's like, what on earth? What am I supposed to do with this? Right? Well, here's one approach. Forget all the negative signs. Do the calculation. As long as there's no adding or subtracting involved, the minus signs can be taken care of later. So leave out all the negative signs, calculate your thing, and then think about it. So if I left out the negative signs here, I'd end up with positive 32.79 or 33 grams. And I'd say, well, is the sign of that reasonable? Yes, a mass has to be positive. So I'll just leave it at that. If I was calculating the energy released, or the energy associated with something, and I've just ditched all the negative signs, and I come up with this positive number, then I have to ask myself, well, what's the question saying? It's saying how much energy is associated with. That's not telling the direction. So then I need to think about it. Is the reaction losing this energy or gaining it? And then slap a sign on it. Does that make sense? So that's a different approach. 33 grams and 99 grams. Okay. What did I screw up? Let's find out, because that's disturbing. Oh, I bet I forgot to multiply by 4. Yep, that's what I did. Yep, I forgot to multiply by 4. So easy to do. Okay, let's fix that. So multiplying by 4, like it said, is 93.43 grams, which is 99 grams. Let's see, a lot of the things that we're doing with stoichiometry, these relationships have a 1 on one side and a number on the other side. And so then I get used to just doing one thing for each fraction, and so I often overlook that 4.